Okay, so we are now going to be going into section 7.2. 7.2 deals with direction fields and Euler's method. Okay, so let's talk about that a little bit. Let me bring up the ebook. Okay. So, what is a direction field? All right. Okay, so let's talk about that. Now, you know, again, the issue we have right now is that we have these differential equations, but we can't find solutions to the differential equations. But we still want to know what solutions look like. Well, one way to see what solutions or a family of solutions looks like for a differential equation is to look at something called its direction field. Okay, in other words, for this differential equation, y prime equals x plus y, okay, for this differential equation, we don't know a formula for the solution, so how can we possibly sketch its graph? Okay, well, let's think about what the differential equation means. The equation y prime equals x plus y tells us, I'm highlighting all of this, the equation y prime equals x plus y tells us that the slope at any point on the graph is equal to the sum of the x and y coordinates. Okay, so for instance, for this differential equation, y prime equals x plus y, since you're saying that the solution has to pass through the point 0, 1, when x equals 0, y equals 1, that's what that, you know, y of 0 equals 1 means. You put it in pink there. The curve has to pass through 0, 1. But its slope there has to be equal to 0 plus 1, which equals 1, because the derivative y prime equals x plus y. So when x is 0 and y is 1, y prime is 0 plus 1, which is 1. And what they do is they have a figure here. In figure 2, they draw a line at the point 0, 1. Now this is in figure 2 here. Okay, they draw, let's see, I don't know if I can't highlight that, but in figure, that's fine. In figure 2, they've drawn a tangent line, okay, because, you know, remember when you have a derivative is the slope of a tangent line to a function at a certain point. The point we're talking about is 0, 1. So that means that a tangent line to the function at 0, 1 would have to have slope 1. And that's what they've drawn in figure 2. Are there any questions on that? Are there any questions so far on this idea? All right, well, we've drawn one tangent, and the solution curve for well, yeah, this initial value problem here, y prime equals x plus y, where y is 0 equals 1, is going to correspond to a solution curve that passes through 0, 1. But if you don't, I mean, but you know, you could find the slope. You know, if you like any solution to the differential equation y prime equals x plus y has to satisfy the differential equation. So you see, in figure 1, they have a slope drawn at a point in the first quadrant, and then they have a slope drawn at a point in the second quadrant. Now, it's interesting. The slope, like they just pick a point in the first quadrant there, in figure 1, and they draw a slope and they draw a tangent line and its slope's positive. Okay, why would the slope need to be positive? If you're drawing, why would the slope of a tangent line in the first quadrant need to be positive? I mean, they just drew a tangent line with a positive slope. Right? I mean, why didn't they draw a negative slope? But what's going on? Why must that slope be positive? And also look in the second quadrant, the slope at the coordinate x1, y1. Okay, that equals x1 plus y1, of course. But they have the tangent has a negative slope there. I mean, why would that be? Okay, Adriana says, very good. In the first quadrant, your coordinates are both positive. So since y prime equals x plus y, y prime would have to be positive. The derivative with a slope would have to be positive in the first quadrant. Okay, but this second quadrant, if you look at x1, y1, let's see, x1 is x1 positive or negative? And I'm looking at the second quadrant, the coordinate x1, y1. Is x1 positive or negative?
Negative.
It's negative. Y1, is y1 positive or negative?
Positive.
Positive. Good. Good. Now, which is bigger? I mean, which has like a bigger magnitude, the negative x value or the positive y value? If you look at that point there, x1, y1. That's right, Rodrigo. The negative x, the negative x is going to overpower the positive y because x is further away from the y-axis. So that's why the slope's negative there, and the tangent line has a negative slope. And you see, what you can do is you can find a lot of points. You can find a lot of points in the xy plane, and then figure out what the slope is at each of those points, because you know what the derivative is. And when you draw all these tangent lines, okay, that have the respective slopes at each point, you get something called a direction field. And that's what they're showing in figure 3. And in figure 4, they show the direction field, but they also have a solution curve on the direction field in figure 4 here. All right, are there any, and you notice the solution curve. That's the solution curve for the initial value problem where y prime equals x plus y, and then y0 equals 1. So the solution passes through, the red solution passes through 0, 1. And you notice that the solution follows the direction field. You see that? How the solution follows the direction field in the picture? It doesn't go against the direction field, it has to follow it, because the solution has to obey the tangents. Every little line segment in there is a tangent line at a certain point. And the solutions have to obey their tangents. How many think that's absolutely cool? Okay. Over here. Okay, so ignore that. That's just a telemarketer wanting money. All right. Thank you, Tina. You like it? And are there any questions? Okay, well then let's go down a little bit more here. So the general form of a differential equation is going to be y prime, dy dx, equals some function f of xy. That's the general form of a differential equation. And we're going to make use of that a little bit later. But in example 1, they say sketch the direction field. Sketch the direction field for this differential equation. Y prime equals x squared plus y squared minus 1. Okay, and then part B says sketch the solution curve that passes through the origin. So, okay, how are we going to sketch a direction field? Well, you got to pick some xy coordinates, and that's what they've done. That's what they've done, as you can see in this table here. Let me see here, one moment. In this table, okay, they start by computing the slope at several points in the following charts. So, like they have the coordinate -2, 0, and the slope at that point would be 3, because if you take -2 squared plus 0 squared minus 1, that's going to equal 3. Okay, and then they pick another point. They pick -1, 0. They pick that coordinate, and then they compute that the derivative at that coordinate is 0. And again, if you just substitute in, to the hold on here. If you just substitute your xy coordinates in the differential equation, you'll get 0. And they keep doing this, and they're picking enough points so that you can graph a direction field. But let's go ahead and look at the first 3 points. Negative. Well, first, are there any questions on that before we move forward? All right. Well, now let's look in Figure 5 at the direction field. Okay, but let's just focus on the first 3 points. So at -2, 0, the derivative is 3. Look at -2, 0, the coordinate -2, 0 in Figure 5. Look at that point, and look at the tangent line at the point -2, 0. What's the slope? What's the slope of that tangent line at -2, 0? Is it positive or negative? That's right, Michael. That's Rodrigo. That's right, Justice. It's positive. In fact, it equals positive. What's the slope of the tangent line at -2, 0? What's the value of the slope? Has to be 3. Good. Okay, well, let's go over to the coordinate -1, 0. -1, 0, that coordinate, they drew a tangent line at -1, 0. The tangent line seems to look flat. Looks flat to me. Does it look flat to you? At -1, 0? Why would the tangent be flat there? Why would it be horizontal? 0 slope. That's right. Very good. Very good. Well, all right, let's go to the origin. The origin, they draw a tangent line there. What's the slope of that tangent line? -1. And you can see it looks like -1. Okay, very good. So all they're doing, it's not rocket science, although it's needed for rocket science. All they're doing is drawing tangent lines, and enough of them, you get an idea of what the direction field is. Okay, and of course, you could draw then solution curves on your direction field. You could draw solution curves. Okay, so if you wanted the solution that passed through the origin, in figure 6, the solution curve would have to be that pink solution curve. Okay, and you can even draw multiple solutions, right? Well, if you know the direction field, you can draw multiple solutions on the direction field, and you see in figure 8, all the solutions have to follow the direction field. Sometimes it's called a slope field. Okay, isn't this is kind of cool, right? How many think it's I don't want to say the word frosty, because I notice students in my Calculus 1 class, when they're a little nervous about a problem, they call it frosty. But I guess I won't go that. Hopefully it's not frosty, but is it kind of cool? That's what I'm. Maybe I get a few thumbs up if we're. Getting a little worried here. Okay, cool, but all right. Well, you know what? Tina thinks it's cool, but she doesn't want to draw it herself. Well, I'll tell you. You see, we have like computer programs that can draw these direction fields. Like when you go into Math 282, you have to take differential equations. There'll be a program that you can use to graph the direction field. But at this stage, we're not. Basically in the homework, you're going to have problems. Well, let me show you a type problem you'll have. Okay, hold on. Let me bring up the example. One moment. Are there any questions before we move on here? All right. Okay, let me bring up something from section 7.2. Let me bring up a good example here. One moment. Good. Okay, just give it a moment. I'd like to do an exercise involving direction fields with you. And okay, good. So let me share that. Okay, now this I don't want you to copy all this down. Okay, I don't want you to copy all this down. This is not to copy down in your. It's in the recording. You can copy it down later in your notes if you want to, but that's not really the purpose of this. What I'm doing here is I'm giving you 4 differential equations. 4 differential equations. A, B, C, and D. And what I'd like you to do is I'd like you to match the differential equation with its direction field. So there are 4 differential equations and 4 direction fields 1, 2, 3, and 4. Think about the so let me just maybe give you a little help on the first one here. Okay, so the first differential equation is y prime equals 2 minus y. It's an autonomous differential equation. Y prime equals 2 minus y. So, I feel like, Tina, like probably many of you, I don't want to be plotting 20, 30 points to figure out what my direction field looks like. But maybe I can think of like a nice value that could help me. I mean, what if dy dx equals 2 minus y, what might be an interesting value of y? What might be a very interesting value of y that we could think about? Oh, Rodrigo says 2. And why, Rodrigo, are you saying let y is 2? Why is that value for the differential equation in A here? What's interesting about letting y equals 2? Y prime would equal 0. Very good. Very good, Rodrigo. So that means that for this first differential equation here, when y equals 2, when y equals 2, this would imply that y prime equals 0. So y equals 2 is special solution. What kind of solution is that? Solution that makes the derivative equal to 0? There's a special name for that. We just learned it. That's called a, well, that's right. It's an equilibrium solution. We call it an equilibrium solution. So, all right, I look at the 4 pictures here. I'm thinking about y equals 2. Y equals 2. Now, is y equals 2 a vertical line or a horizontal line?
Vertical.
Y equals 2 would actually be a horizontal line. And I welcome all answers. Nothing wrong with, So y equals 2 is a horizontal line. So I got to look on these graphs here. And when y equals 2, y prime equals 0. So that means along the line y equals 2, the slopes need to be what? 0. In other words, along the line y equals 2, slopes need to be flat. Okay, well, let me see here. Let me take a look here. Let's take a look. So here's y equals 2 on the first direction field. Do the slopes look flat along y equals 2, along that line? Are the slopes flat? They are. They are. Okay. Well, let's go now. We're looking at A. Let's go to the second. Roman numeral 2. I'm going to draw the line y equals 2. Okay. Nell, you're good with that, right? Good with that? Are the slopes flat? Excellent. Thank you. Are the slopes flat along that line? No. So that means 2 is not going to be a candidate. 2 is not going to be a candidate for choice A. We have to take our time with these problems because, of course, in WebAssign, they like matching, so you only got like a couple of tries, 1 or 2 tries. Right? Okay. so basically one is a possibility, but two's out. What about three? Is three a possibility? Yep, it's a possibility. What about four? No. So that means for choice one, for A, it's going to be either one or three, but it can't be both. So now we'll look at B. We'll look at B. Okay, and think about B here. Okay, what are the equilibrium solutions for B? What are the equilibrium solutions for choice B? Hold on. One moment. I saw a couple. Okay. Rodrigo says 2 and 0, but could we be more specific? Okay, x equals 0, right, Michael? And y equals 2. So, okay. Well, since for the second one, for B, when x equals 0, or y equals 2, okay, that's going to imply for B that y prime equals 0. Okay, well, now that means that for choice for B, it's going to either be choices 1 or 3. And which choice would it have to be? Okay. What do you think? Tina and Michael think 1. Does anybody think choice 3? Rodrigo thinks 1. Well, let's take a look here. Let's take a look. So x equals 0, that would be, is that a horizontal line or a vertical line? Vertical. So, okay, I'm going to draw x equals 0 right here. Okay, there, do the slopes look flat along x equals 0? They do. So, okay, but for choice 3, Roman numeral 3, are the slopes flat along x equals 0? No. So basically for choice for B, the answer is going to have to be choice 3. And for A, you'd have to have choice 1. And this is the kind of thinking you have to do. This is the kind of thinking you have to do for this kind of question. Okay. All right. Now let me just give me one moment here. Give me one moment. Just one moment. Okay, one moment here. Hold on. All right. So what I'm going to do here, I'm going to stop the recording here. But are there any? So I didn't finish this, and I didn't finish it on purpose because you're going to see this in your homework. You're going to see this in your homework, and I don't think you want me to take all the fun away, right? For this problem, right? Right? I don't think you want that. You want to think of now. You have the. I think you have the hang of it. So let me stop the recording.